Now that we've talked about how to create a line of best fit, we need to move on to this idea of a residual and the concept of a residual plot and what information you can get about your linear model from a residual plot. So let's start with the idea of a residual itself. The word residual sounds a little bit like residue, which is really what a residual is. It's just what's left over in terms of the y values from your model. So here I've made up a data set with a few points in it. I've also found the line of best fit using our least squares regression method. And as you can see, I've given the equation for that line of best fit. But if you'll notice, as with just about any scatter plot that you create, not a single one of our data points lies exactly on the line. In fact, some of the data points, like this one right here, they're relatively close to the line, while others are a little bit farther away. And those vertical distances that I'm drawing right now, each of those, that's not very good, each of those is the residual for that given point. It's just the distance from your point either down to the line of best fit or up to the line of best fit, depending on whether your point is above or below the line. So right here would be the residual. That's not going to fit. So the idea of a residual is pretty simple, and it has a simple formula to find it. A residual is simply found by, sorry for that pause. A residual is found by taking the difference between your observed y, so the y value you get from your point, which would be whatever that y coordinate is, and you just subtract off your predicted y that you get from your line of best fit. So in symbols, the residual is your y value from the point minus y hat for that given x value. So like I said, the concept of residuals is not very difficult. It's just that vertical distance between your point and the line of best fit. So let's move on and talk about what a residual plot is. So in a residual plot, of course, you're going to have to take each of your points from your scatter plot and find the residual for it. So what I've done in this table that you see is I've written out the x and the y coordinates for each of the points in the scatter plot that you saw on the last slide. So all 6 points. I've given you the x and the y coordinates. And then what I've done is I've taken each of the x coordinates and plugged that into our line of best fit so that I can get y hat for each of the various x coordinates. And once I have that information, y and y hat, now that you've seen how to find a residual, we can calculate the residuals for each of our 6 points. So let's go ahead and do that. So we know that our residuals are y minus y hat. So for this first point, I need to take 2 and subtract off 3. So that gives me a residual of -1, of course. There we go. For the second point, our residual is going to be a positive 1.5. For the third point, it's going to be -1/2. For the fourth point, we've got a residual of 2. For the fifth point, we've got a residual of -1.5. For the next point, we've got a residual of 2. It looks like I can't count. We've actually got 7 points, not 6. But for this last 7th point, we've got a residual of -1.5 again. Now that we have all of our residuals calculated for each of our data points, we can go ahead and create our residual plot. You'll notice over here that I've already got the plot set up. On the horizontal axis, we just have the same scale that we had for our scatter plot. We're just going to use our x values again, like we did on the last slide. But our vertical axis is going to be using a different scale, and of course that's where we're going to use our residual data. So again, I'm using the x coordinates for each of our data points, and then I'm going to plot that against each of the points' residuals. So on our residual plot, I'm going to plot the point 1, -1 first, and then we've got 2, 1.5, also 2, -1/2. we've got the 0.32, the 0.4, negative 1.5, the 0.52, and the 0.6, negative 1.5. So there's our residual plot. And you're probably thinking, well, that's lovely. What is the purpose of this thing? If you remember back to chapter 2, we talked about creating normal probability plots, and we were able to use those normal probability plots to help us determine if our data set was truly modeled by a normal distribution. If you remember, in that case, our rule was that the closer that the points in our normal probability plot fell to a straight line, the more normal our distribution was. We sort of have the same thing going on here, only our rule is a little bit different. We're going to use this residual plot to determine whether or not a linear model is actually a good representation of the data we were given. Now, if you remember what our scatter plot looks like, we'll go back to refresh your memory. It looks from the scatter plot like a linear model is reasonable for this data set. If I pull up my regression information, we know that we've got an R value here of 0.507. So it's not a particularly strong linear relationship, but it's certainly positive. Maybe we could call it a positive and moderate linear relationship. So that gives us some sort of sense that a linear model might be appropriate. But our residual plot gives us a little bit more information as to whether or not we can reliably use a linear model to represent our data. And the rule for this is that if you see no pattern in your residual plot, that it looks just sort of like a chaotic jumble of points, then you can say that your data can be reasonably modeled by a linear model. However, if you see some sort of pattern in your residual plot, then a linear model is probably not going to be appropriate for your data set. So I'll give you a couple of examples, and there are some more examples in your book as well. Just bear with me a moment.